Alright, let's look at example 16.15. We've got this spool and it's attached at point A where it has radius 1. And we're concerned about the motion of a different radius 2, which is where point B occurs at. We want to find the acceleration of B, and we're going to do that knowing the initial angular velocity and angular acceleration. They give that to us. Okay, from that, let's figure out what G is doing. We can figure out, I'm sorry, not B, what the acceleration of G is, because we have, draw a bigger circle. If it's attached here at A, and here is G, then G is going to be moving perpendicular to A at that moment. The acceleration can then be found just by doing alpha times r. And alpha for the whole spool, regardless of the radius, is 4 radians per second. The radius is 0.5 feet. So I get the acceleration of G as 2 feet per second squared. Alright, that's this point right here. We have its acceleration. Alright, that's going to be our translating point, and we need to now figure out the motion, the motion up here on point B on a different radius. So this is going to be rotating and translating, and we'll be using G as our translating reference point and then analyze the acceleration due to the rotation about G. Alright, we have an acceleration equation. The acceleration of point B is going to be equal to the acceleration of G plus alpha, vector, alpha crossed into r of, we want B with respect to G in this case. I'll draw that in a second. Minus omega squared r of B with respect to G. B with respect to G is going to be the vector right there. So r of B, when we're looking at it from G, we're given omega, where we know this vector. So what is the vector r of B with respect to G? Well, r of B with respect to G, we can say it's just got a positive J component, and it's 0.75 feet. Okay, what else? Let's go ahead and plug some stuff in. The acceleration, go ahead and assume that B is going to have an X component and a Y component. So that's this part right there, just the acceleration of B. Now for the acceleration of G, we know it only has a Y component, it's negative 2J. For the cross product, alpha is in the counterclockwise, or sorry, alpha is going to be in the clockwise direction. Same with our omega, just by looking at it. So I'm going to give that a negative 4k. And we're going to cross that into the radius the vector 0.75 J. Alright, then we have the omega squared r of B with respect to G term. They gave us omega, so we can plug that in as 3 and then square it. And then using the same vector r of B with respect to G, that's the direction that this term of acceleration is going to be pointing in. Alright, now we just put, in my words, circles or one color around the I components. If we take this cross product, we'll have a, b, x in the I direction plus a, b, y in the j direction. That's equal to -2 in the j. Plus, if I take k and cross it into j, k crossed into j is going to give me a -I, so this negative and negative is going to give me a positive 4 times 3/4, so the 4's go away, so the 3 in the positive I direction. And we get a minus 9/4 in the j direction from this term. Sorry, I had to do that in my head real quick. Equating the like components, we have an I term, we have another I term, we have a j term, and a j term. So for the x components, we have the acceleration of b in the x is equal to that 3 feet per second squared. And the y, we have the acceleration of b in the y is equal to that -2j minus 9/4 j. And we can add those together to get a -9.25 feet per second. Okay, that is something that is 3 long in the x direction and 9 long, or -9.25 in the y. So our acceleration vector looks like this. We wanted to find this angle. We could take 360 and subtract the tangent inverse of 8.75 over 3. I'm sorry, this is 8.75. The final answer is 9.25. So 8.75 over 3, that's our y component of our x component. And you can find the magnitude as the square root of 3 squared plus 8.75 squared, and that's 9.25 feet per second squared. Alright, that's our final answer.